But now you know where we're coming from, and you can have a think about those arguments and if you agree with them or not for later. Okay, so our founders have a pretty impressively long experience of AI. So Luca and Mons, the founders, have over 15 years experience of building and implementing AI projects. So their vision with Peltarion is to make it possible for people from different backgrounds to build and implement AI solutions, which was why they started the Peltarion Platform. And their experiences also give us a pretty interesting insight into what types of problems it is that customers want to solve, which we've put into this platform that we're going to be working with today. So now you might wonder, how can one build a model without code? And this is exactly also where the platform comes in, which I myself think is pretty great. The platform makes it possible for people without a coding background to create and change AI models. So now even someone like me, I'm a historian by background, can build an app that can, for example, diagnose asthma based on someone's cough, or predict the likelihood of customer churn based on someone's message in the customer service chat. Right. What does AI mean? One thing that I didn't quite understand when I got to this field was how it's possible that one type of technology can have applications that are so wide-ranging. Is it just if we build sort of a superhuman artificial general intelligence that these applications exist? Or if not, how does the AI technology that we have today actually work? The answer is that AI is what I spoke about before, a so-called general purpose technology. And this means that the things you can do with AI are so all-encompassing that you can expect basically every field, every industry to be able to be made more efficient with by applying AI. We're going to go into a little bit more exactly what that means now, I think. So for context, it can be helpful to look at some other big technological disruptors, just to try to conceptualize a little bit more what this actually means for us in the coming years. So in the 50s, the transistor came about. Before the transistor came in, there was even a profession, probably a professor too, but a profession called being a computer, which was someone whose main job it was to be making calculations for a living. And when the transistor came around, the cost of doing calculations was reduced so significantly that it dramatically changed the course of history. The second major disruptor was the internet, which dramatically reduced the cost of distributing information. So just think how big a difference it makes now when we use the internet instead of the post office, where it takes just a few milliseconds for us to reach, to make information reach across the world. And thinking of the internet also leads us quite nicely onto the topic of AI, because with the increasing availability and generation of data, a fundamental building block for AI has also been created. So suddenly there's enough data out there to train data-hungry AI models to make predictions. And this is exactly why AI is so significant. AI reduces the cost of making predictions and can therefore be expected to disrupt everything that in some way has to do with predicting things. Things like the weather, energy demand, political outcomes, maybe even human behavior. Let's look at a few concrete examples to get a sense of what this means. So let's say that you are a music streaming company and you receive thousands of new tracks every day. And every day you have to decide if it's punk or rock or indie or classical music, so that it can end up in the right category on the website. This can be automated so that an AI model uses music that is already classified according to its genre, or maybe also according to its mood, and uses that information to classify new music without a human even needing to listen to the tracks. Or if you train an AI model that can detect the difference between a malignant and a benign skin lesion. This is based off a company that's built a model that can do this with the same accuracy as a dermatologist. So this means that we can make many, many more diagnoses of these conditions than was possible before. And it also means that we can make it really simple for someone to just take a photo of their birthmark or of their skin lesion and find out if they ought to see a doctor about it or not. At the same, in a sort of similar way, the models around diagnostics are also getting really sharp. And we've now, or people have now found that several models are actually better than the radiologists themselves. What's been done to achieve this is that the model has been fed not only with the radiologist's sort of diagnosis, so it's not just the radiologist that looks at the image and says yes or no, but it's also been fed with data from further along the patient's path. So if the patient later gets sick, that will be fed back and associated with that image as well, which is how they've been able to achieve a performance that's actually higher than a radiologist in this case. And you can also train models that can recognize how different diseases within agriculture look from satellite images, and therefore very quickly find if a disease is spreading within a field, for example. The thing with this type of technology is that we can't really put it aside or separate it or make a separate sort of AI research and development department within a company, because the applications here are so wide-ranging that we need every single department within a company to think about how they might make AI a part of what they do to make themselves more effective. So this is really the core challenge that we at Peltarion, but also all the companies that we're working with, are facing. So how do we make sure everyone can start taking on this challenge? And one of the things that back us up that we're sort of on the right track here in terms of, you know, the more AI, the better, is that if we look at a survey that's done on how companies perceive the benefits of AI, we can see that companies that have 11 or more deployments of AI projects, they tend to perceive a much higher substantial benefit of these AI projects than the ones that just deploy one or two AI projects. So there's a lot to do on many, many different levels within businesses to fully make use of this opportunity. But as we spoke about before, there are two very tangible obstacles for businesses to become so-called AI first or AI ready, maybe before. And the two things here are that there is currently a lack of talent or a lack of expertise within this field. And the second thing is that if you try to do this all yourself, you have to basically bootstrap together various different platforms and make them speak to each other in a nice and secure way, which often leads to quite patchy systems and other problems. So this is a quote from a Microsoft research chief who says that the cost of acquiring a top AI researcher is actually comparable to the cost of an NFL quarterback, which is not trivial, right, in terms of what that costs. This year, the US was expecting to need 700,000 more data scientists than they had in 2017. At the same time, the total at that time was 35,000. So they would have needed a 20-fold increase to actually meet demand, which is not only sort of nearly impossible, but also quite disheartening if you were hoping to just employ someone and be rid of the problem then and there. So what is the solution here? Well, the thing that we are advocating for is that we need to start working with AI and understand the technology so that we ourselves can become AI builders and AI sort of advocates within our fields. But where does one begin? It's not only a big daunting term, but also quite a lot of things to learn. So I thought we'd begin today with the basics. What is actually AI? And then once we've gone through this, we'll go on a little bit more into how you can get started with building it on the platform, and we'll actually build a project ourselves. If you want, you'll be able to follow along during the webinar, but I'd probably recommend doing it afterwards, and I'll send you an article where you can follow along. So by the time you leave work today, you'll be able to say that you built your first AI model, and I hope that sounds exciting. Okay, but let's start with this. What is AI? So very broadly, AI is making machines exhibit intelligent behavior by making them able to make predictions. And in the early days of AI, the way that this worked was through a series of hard-coded logic. So if you've been working in Excel a lot or you've been programming, you'll recognize the idea of using if-then statements to create sort of a big decision tree. And this was basically how AI worked in the 50s through to the 70s. So, these days, whenever I'm stuck in an Excel spreadsheet, I just comfort myself with the idea that I'm doing what cutting-edge AI scientists were doing just a few decades ago. But in the 80s and 90s, the field of machine learning emerged. And machine learning is a subset of AI that basically removes the need for you to have to code the program yourself. This might seem a little bit counterintuitive, but the way that it does this is that it has a set of data points and an outcome connected to each data point, and then it asks the machine to find a pattern that represents those data points and how they relate to that outcome. So kind of like this. The difference to traditional programming lies in what the computer actually does. So the machine will then, within machine learning, the machine will then do this by testing different weights for each of the data points, and then seeing how that affects the accuracy when predicting the outcome. So for example, it will test, here we can see W1, W2 on these lines here. It will test different weights to weigh the impact of these features, and then see how that affects the outcome that it has. So it will then attribute a lot of weight to a feature that's important and a smaller weight to features that aren't. What that means then is that there's very little coding in AI. The algorithm is determined almost entirely by the data that you put into it. So if you're using bad data, then what you get out is also a bad algorithm. Or if there's a pattern in your data that you didn't consider, that you didn't want the model to focus on, then it may very well still look at that pattern to determine the outcome. So a good example is, for example, a research group was looking at whether you could diagnose pneumonia from x-rays of lungs. And they had a bunch of images with x-rays of people who had pneumonia and a bunch of images of people who didn't have pneumonia. And they put this into a model to see if it could determine which ones, if it could diagnose these people well. The problem was that when people were suspected of having pneumonia, they were often x-rayed in their hospital bed, so that in the x-ray images, there was a little frame of a hospital bed that you could see. And what the algorithm then ended up learning was that if you were in a hospital bed, you definitely had pneumonia. So it spotted a very different pattern, which then was not at all what the researchers wanted it to spot, right? So it's very important to be aware of the type of data you're using, because that will definitely show up in what type of model you build. Okay, so let's look at this in a little bit more in a bit more of a sort of pedagogical explanation. We're still on the machine learning part, but we'll get to deep learning very, very soon. But let's say you're looking at house prices in Stockholm, for example, and you want a model that will be able to tell you the relationship between the area of the house and the distance from the city center and how these relate to the price that it sells for. So you have these data points, but instead of trying to find the relationship between them yourself and write down the logic in a computer program, you ask the machine to find the model which it thinks best fits the data points based on a bunch of data about previous house prices. So it will then do this by testing different weights for each of the data points and then seeing how this affects the accuracy when predicting the price. So for example, it might realize that living area is extremely important for determining the price, while the distance to the city center really doesn't matter that much. And it will then attribute a lot of weight to this feature and a negligible or no weight at all to the data point with the distance to the city center. So eventually it will come up with a function that describes the relationship between the data points in a multi-dimensional space with as many dimensions as you have inputs. So in this example, I only had 2 inputs, but you can imagine that this becomes quite a lot more complex if we add in more data points. We get a function with many more dimensions. Those of you who've done some statistics will recognize this. A lot of machine learning is actually based on statistical methods, and this example, for example, which is a linear regression problem. But what this means is essentially that instead of writing in the logic that you want the program to follow, you let the machine find that logic by itself by feeding it a lot of different data points. Okay, so now we've broadly covered how machine learning works, but within this field, we've also got the most recent hype, which is deep learning. So let's briefly talk about the difference between these for a second. Machine learning is really good for working with tabular data. So by this, we usually mean any data that can easily be represented numerically, like in the house price example we were looking at before. But there is a lot of other data out there that isn't numeric. So you can think of images, for example, or videos or sound, and not least the text I'm saying as I'm delivering this webinar. But it would be very difficult for us to represent those things numerically. How do you assign a number to represent the meaning of a word, for example? And what about words that mean very different things in different contexts, like river bank and bank account, for example? Oh, sorry, can you still see my screen? Okay, thank you. All right, okay. So the great thing about deep learning then is that it opens up the opportunities to both represent and use what we call unstructured data. So this is all of the data that we've just spoken about, basically any data that isn't numerical. So this means that the text I'm saying right now can be both represented numerically and then used as data to make predictions. So what both machine learning and deep learning have in common is that they approximate functions to represent large data sets. So you can see here they're in the same, deep learning is a subset of machine learning, and they both do approximate functions that represent data sets and the relationship between these different features. But the main difference is that while machine learning is great for tabular or numeric data, deep learning is usually better for working with unstructured data because it can deal with the inherent size of it. Okay, I will get in a little bit more to what deep learning means in a second, but now it's just good to grasp these basic 3 concepts as ideas in your head. So as a quick summary, with machine learning methods, computers can take data and learn to make predictions with it. With deep learning, computers can both represent data and make predictions based on that data. And finally, machine learning and deep learning methods approximate functions for very, very large data sets. Okay, let's dive in a little bit more into deep learning and how this works. We'll return to this familiar image illustrating the difference between AI, machine learning, and deep learning, and then zone in a little bit on this one here, deep learning. So in the last bit, I talked a little bit about how deep learning is powerful because it can represent unstructured data. But now we're going to look at what it means to actually represent unstructured data in numbers and what this enables us to do. So if we look at this pretty low resolution image of a handwritten 5, we can start to get a sense of how big a data point this actually is. So this little 5, if we represent it numerically, ends up having a lot more dimensions than the house price regression problem we just briefly looked at before. So in this 28 by 28 pixel photo, each pixel gets 3 values to describe the color, or more specifically, to describe the amount of red, green, and blue that this pixel has in it. So this means that this tiny image becomes 28 by 28 by 3 data points, so 2,352 data points, if we were to use it in a computer program. So if we want to use this in an AI model, that would mean that instead of the 3 dimensions we looked at in the house price example, we would need 2,352 different dimensions for the model to work across. So it's a pretty significant increase in the size of data that we're looking at. So how does deep learning do this? How does it approximate functions that are so large? In most cases, you'd work with data that was bigger than a 28 by 28 pixel image. So how does this work? It sounds huge, right? Like extremely computationally heavy. And it is, but it uses a method called deep neural networks. And what deep neural networks are is basically the means for finding the function that best fits the data set. So in this slide, I've referred to them as nonlinear function approximators, because they help us approximate the nonlinear function that we need for the data set that we've given it. So if we look at this slide and we imagine that W1 and W2 here are tunable weights, this is a representation of a very, very small neural network. And we feed in this tiny neural network R5. The network would process the image by applying different weights here to determine which features are important for predicting the outcome. And it would then make a prediction. If it got the right result, it would keep the weights, and if it got the wrong result, it would adjust them. Now, as you might imagine, looking at this, training a model from scratch requires a huge amount of data. So training a network from scratch with image data can require anything from 10,000 images to several million images if you wanted to get a really good result. But lucky for us, we don't always need to train a network from scratch in order to build a model. In fact, in many cases, there are pre-trained models that we can begin with because many companies and individuals release pre-trained models that they've built for us to sort of just fine tune. And what that means then is that a pre-trained model already has some weights in the network based on previous data that it's seen. So it already has what we call biases in it based on other data that we don't necessarily need to supply it with. So this is really quite helpful for us when we build models, is that we often have a range of different models to choose from, which means that we can work with slightly smaller imaged or text data sets. Another thing to be aware of is that there are many different architectures for neural networks. So what I showed you before was a very simplified neural network, but there are many, many different ways of designing these based on what type of problem you're solving. And a lot of what data scientists spend time on is reading about how other people have approached similar problems to the one that they're tackling to find out what works best. So for example, for processing images, a network architecture called convolutional neural networks, or CNNs, are the most common. And this is because the assumption behind this network is that pixels that are close to each other are likely to be related in some way. So this makes a lot of sense in an image. And for this reason, the input values that are close to each other are multiplied together in a series of convolutions. This illustration is helpful for just visualizing how this works in a convolutional neural network. But we don't need to dig deeper into this for the moment. It's a little hard to take in before you've started building your own models and experimented with different problems. So for now, it's just important to note that there are a lot of different ways of building neural networks, but that most of the time you'll be able to use an architecture that someone else has built as the foundation for your model. And you can also choose to use a pre-trained network as well. Okay, I realize this is a super speedy introduction to deep learning, but the rewarding bit comes very, very soon, because then we'll actually get to build some stuff. So I hope you're staying with me. You're all very brave to dive into this so quickly. Okay, so what are the key takeaways so far? with deep learning, we can represent and use unstructured data, right? Two, training a network from scratch requires a huge amount of data, but using a pre-trained network, we can have less data and still get a good results for the models that we build. And finally, there are many different neural network architectures out there that we can use, which help us with our projects. Okay, let's get building. So this is where you can make the choice either to follow along on your own laptop, or you can just watch me do this for now and then do it later. There's an article on our website called 5-Click AI, which I personally think is a really good sort of introduction to it, because it literally is just, well, it's actually 10 clicks, but I think you can manage. So within 10 clicks, you'll actually have an AI model. So it's a good introduction. But yeah, for now, I'll do this on my laptop, and then you can follow along either now or later. So for this project, we're going to be working with text data to see if we can build a model that can distinguish between tweets that are about real disasters and tweets that aren't about real disasters. So for example, if we have a tweet that says the guitarist is on fire, this could mean both that the guitarist is amazing, but also that he or she is really on fire, which wouldn't be great. So let's see if we can build a classifier that can be distinguished between these two types of tweets. And we're going to be using a pre-trained model. So here, just a few minutes later, we're already getting some use from what we've learned. So this is, as we looked at before, this is a pre-trained model. It's a network that already has weights built into it. Obviously, it's a lot bigger than this, but again, I thought I'd bring up this illustration as we've looked at it before. And BERT was released by Google in 2018. And the reason that BERT is such a great model to use is that it was trained on over 3 billion words. And that for fine-tuning BERT, we need a lot fewer words to feed into it so that we can get a pretty good result, even with a much, much smaller data set, which we're very happy about. Otherwise, it would both be extremely expensive to train a text model and also very difficult to get the data. So the model that we train, from the moment we hit run after our 10 clicks, it will take about 2 hours. So when you've set this up, you might want to just check back on this later and see how it's doing and see if your results make sense and if it's good. Okay, so the reason the BERT model is so great and made such a big splash is because it did something very different to what a previous model did. So Word2Vec was a very famous model used before, but the problem with that model was that the same words were assigned the same numerical representation. So if you had a phrase that was open a bank account and another phrase that was how is a river bank formed, the word bank in those two sentences would have the same token representation, which doesn't make sense because they mean very different things in those two scenarios. So what BERT does is that it looks at the semantics of the whole sentence, and for these words in these contexts, the word bank gets different token representations. So the great thing here is that with BERT we can work a lot more with semantics and understand the sort of context of the word when we build our model. So what this means is basically that we can design models that look for semantic similarity instead of the exact words. So in this, this is an example from a demo that we built for a company where they wanted to be able to have a search engine where if you put in a phrase, you could get all the similar sentences that they had in their database. Sorry, the similar questions. And you can see an illustration here of why BERT is so helpful, because if we look at the second sentence that the model pulls up, is technology destroying humanity? You can see that this sentence actually has no word in common with the one that we put in. So here, the model is really good at looking at the semantics of the sentence instead of the actual words. Okay, so this is the power of the model that we're going to be working with, and I hope you're excited to get started. Let's get to it. So if you're following along on your laptop, you can go to platform.peltarion.com and set up an account. It may take a couple of minutes for the email to come through because we're quite a lot of people here today. So once you've filled in your details, just come back to the webinar and we'll get started to with the data side of things. So we're going to be using data from a data science competition website called Kaggle. That's Kaggle. And on Kaggle, they gather datasets from a bunch of different companies and other actors to let people experiment. Yes, I can type it. I can send you the link straight away. 1 second. Let's see if I can send it to everyone at the same time. That'd be awesome. Blah. Okay, I sent it to Natalia. Maybe Natalia can send it on to everyone else. I seem to be having some multitasking problems. Actually, yeah, here we go. Here's the Kaggle data. And someone sent the link to the Peltarion platform. That's great. Thank you very much. Okay, so to get the data, you'll need to go to the link I just sent. If you want, you can have a little read about what the data set is like. But otherwise, you can just go on to data here, indicated by the big red arrow on the page, and then download the, there's no promo code. Sorry, I'm answering questions as I go. I hope that's not too confusing. There's no promo code because right now it's all free, so it's completely fine. Okay, so you'll then just download all of the data. There's a button that says download all, which gives you a zip file on your computer. And you'll then have 2 folders in that zip file. There will be one called train.csv and one called test.csv. So the folder called train.csv is the one that we'll be using to train the model. And the folder called test.csv is the one that we'll keep completely separate from the model. And the reason that we do this, the reason we keep one of the files away from the model is so that we can then run a separate accuracy test to see how the model works when it has completely unseen data. Okay, you don't need to do anything else with the folders for now. We'll just briefly talk about what the platform looks like so that you can get started easily. So if you've now set up an account, you should, if you click on projects in the top left corner, be able to get a yes, I'm very sorry that Kosovo is not in the countries list. I will sort that out as soon as I can. For now, if you could choose another country, that'd be great. I'm very sorry about that. But if that's okay for now, please do that. Okay. When you get to the platform, you can set up a project. Click on New Project here to get working. So when you've signed in, just click on Projects, then click on New Projects to create a brand new one. Okay, you should now see something that looks a bit like this. In the left icon here, you'll be able to upload the training data. Remember that this is the file called train.csv in the folder you got from Kaggle. So don't use the test file, just use the train data. And you'll now get to this, which is a page with a summary of the data that you've uploaded. And you'll see here on the left-hand side that the data has been divided into 2 different subsets. There's one called training, which is 80% of the data. This is the data that the model will be used for training. And then validation, which is 20% of the data. And this is what will be used to validate whether the model is on the right track or not. So we'll be able to see that in the evaluation page later. The comparison with how the model performs on the training data versus how it performs on the validation data. So if you scroll down to the bottom, you'll get to a field that says target here. And this is the feature that we're going to try to make the model predict. So if you look down here, you'll see that there are 2 different classes. There's a 0 and there's a 1. So a 0 means that the tweet that we fed into the model is not about a real disaster. It's just a funny phrase, or it's just something else. It's not about a real disaster. And then there's a 1, and that means that the tweet we fed in is actually about a real disaster. So we can look here at the split between these two classes and see that it's kind of even. It's a bit more, we have a couple more tweets on them that aren't about real disasters, but it sort of looks even enough. So we can be happy with this as it is for now. If you want, you can also click on this icon up here called table, which will give you a sense of what the data file looks like. You don't really need to do anything else with that at the moment, but it can be good to know just what the different fields, what the different columns are called, so that when you design your model, you don't have to go back and check later. Okay, but since we're happy with the way that this data looks, we can now actually start building. So if you click on Save Version up here in the top right corner, another button will appear which will say Use a New Experiment, and then this guy will pop up, which is the Experiment Wizard. So the Experiment Wizard will guide you through some of the key choices we have to make when setting up this model. So first we'll be asked if we're happy with the way that the data set's been defined. So an 80-20 split, we've already spoken about that. This sounds good to us, I think. And if we're happy with that, we can also, you want to check that it's the right version of the data you're using. But if we're happy with that, we can click next and get to the next part of the wizard. It will then ask you what model it is that you want to use. And in this case, because we only want one prediction for each tweet, so each tweet can only be one category. It's either a disaster or it's not a disaster. The type of problem that we want to solve is called a single label text classification. So when that option comes up, you just approve that. And then it will also ask you what the input and the output features are. So since we want to use the tweet to determine whether it's about a real disaster or not, the input feature should be set to text, and the target feature should be set to target, because that's where the ones and the zeros were. All right, below these fields, there's also a section called recommended snippets, which is where you'll see the BERT model, the one we talked about before. And now that we're sure that this all looks good, we can click next again to move on. The final thing here, initialize weights. You'll just be asked whether you want the weights to be trainable, which you want in this experiment, and then you can click create. Okay, so this is what the experiment wizard brings up for you. We can see that it takes the text as input here. It then puts it through the BERT encoder, and then through 2 dense layers to finally predict the target. And there are no sort of nasty error messages popping up here on the side. So this all looks good. And I think if we're happy with this, we can just press run. And that's the experiment running for you, training an AI model. Now it's going to take a little while for the model to train. As I said before, I think it'll be up to 2 hours for this one. So I think for now, we're just going to have to stick with my screen. Even if you're doing this on your own, you'll just have to be on my screen for a little while to see what the evaluation looks like. We've got a couple of doodles on the screen. I don't know if that's intentional, but it's please just ignore them for now. Okay. When we've trained our model, we get to the evaluation view. And here we can see a summary of all the experiments we've run and how they compare. Let's see if I can show you my whole screen so you get all of this. Okay. So yeah, here we can look at performance across a variety of different metrics, like for example, accuracy. For this experiment, accuracy is a really good metric. Since there's just one correct answer for each data point, accuracy makes good sense. You can read more on the different metrics as you continue your data science journey. Maybe even in our knowledge base, there's a lot of good explanations out there. But for now, it's just useful to know that there are different metrics that are good depending on the type of problem you're working with. So if you're working with something where you have many different labels for each class, you might want to use a different metric, for example. And if we look in the column of on the right, we can see that this particular model that we designed, for this model we got a 79.8% accuracy. For a problem with just 2 classes, as this one is, we know that anything over 50 will be better than random. So, you know, our model, even with such a simple setup, is definitely better than that. But if we scroll down, we can also look at a loss matrix to see what it is that the model is getting wrong. And once you're in the platform, you can actually click on these as well to see specific examples on of what's going wrong. So I didn't actually do this in my tutorial today. I don't know why, but this would have been a neat feature to illustrate. But please try this out when you're building, because it's really quite neat. So for example, we can see here that there was a pretty high rate of false negatives, and that's instances where there were actual disasters, but the model predicted as not being real disasters. If we were using this in real life, we'd probably prefer something with more false positives instead of false negatives, but you know, that's something we'd probably want to tweak in that case. But yeah, this is a pretty good start. Now would be maybe a good time for us to try to understand if we think we could have got a much better start, a much better result. So my first place to start for this would be to just check back on the data again. How does it look, and is it actually reasonable for a model to be able to spot predictions here? So if we go back to the dataset view up here, we can see that a couple of these tweets are actually quite difficult to understand unless we click at the link that goes with them, which we didn't in this case give our model the means to do. So yeah, there might be a couple of examples that are actually really, really difficult to understand. And if we do a proper analysis, we can also see that there are actually a few tweets that appear twice, but that have different classes every time they appear. So once they appear with a 1 and another time they appear with a 0. So there also seems to be some problems with the data set, which we might want to tweak to get an even better result. But with that said, there are a few things we can try in the modeling view to see if we can improve it. So let's just explore these quickly for a second. If we go back to the modeling view up here, you can click on settings up here in the top right corner, and you'll then see a few different fields like batch size, epochs, and a bit further down you'll also see this one called learning rate. Let's start by looking at learning rate. What this is basically the extent to which the model iterates with every step. So what the model is asking you here is, with each new piece of information I get, how much do you want me to adjust the weights in the model? And when you'll notice here that the learning rate is very, very low here. And the reason for this is that when training BERT models, the experiment wizard that we use to set this up automatically gives us a very, very small learning rate, because BERT has already been trained on an extremely large amount of data. So if we set the learning rate to be really high, then we undo a lot of that learning that's already gone into the model, which isn't great. So we only want the model to tweak its weights a little bit with every new piece of information. But now that we've trained our first model, we might want to try to tweak it to get a better performance. So you can see here in my different experiments, I've tried with a couple of different learning rates to see which gets the best results. The second thing we can explore is batch size up here. The batch size is the number of examples used in one so-called training session. So how many pieces of data does the neural network look at one time? So you can try to reduce this a little bit, because this number is quite high, maybe to 12, and see if there's an improvement. And then finally, there's also this figure here, which is called epochs. So if you try increasing this a little bit, what epochs means is basically the number of times that the model goes through the whole data set. So right now it looks at the whole data set twice. If we increase it to maybe to 4, then it will look at all the data 4 times. So I think I've just given you the settings that I did to get the best results. So if you paid attention, you'll maybe get slightly better results. Yeah, okay. I hope you realize now that you're building real AI models with me. It's pretty cool. Less than 2 hours since you started. No, less than 1 hour. This has been a really, really speedy run through. Less than 1 hour since we started here. we're now working with some pretty advanced methods. And while you might feel like there's still a lot left to learn, which, you know, you're not wrong about, data science is a rabbit hole that you can spend a lifetime in. So with this webinar, if you followed along, you're now a good step along the way towards understanding it. So really, really great work, everyone. Okay, before we finish and get on to some questions, we're going to try one last thing, and that is to test our models for ourselves. So if you click on the final button here in the top menu, you'll get to the deployment view. So here you can choose the model that did best and start using it in real time. So for example, if you want to monitor a Twitter feed to flag instances in your district where there might be ongoing disasters, you can deploy this model and just do it and it will, yeah, you can deploy this model so it will do it for you. So if you just click on new deployment here and choose the experiment which you think did best in the epoch where the model had the best performance, and then click enable, you'll then be able to click on this button called test deployment to get to a page where you can test the model with different examples. Okay, so if you type in a text on the left here, you'll be able to see what the model predicts for it on the right. And the first time you call the model, it will take a little while to load, and I will say this phrase querying API here before you get to see its predictions. Okay. Let's see what it predicted for the world is going to end. Yeah, so for this one, it predicted a 0. It said, no, the world is not going to end. This is not a real disaster. You're being silly. And that's it. So you've now built a model with the help of our friend BERT here that you can start to use in real time. Congratulations, everyone, for building your first model. Okay. So to keep exploring, you can go to platform.peltarion.com. And if you want, we also have a mentoring program. So if you get somewhere, you start exploring, you realize that, you know, this is something I want to keep going deeper with, and I have a good project, then you can also apply to our mentorship program, which we have here. So peltarion.com, data science mentorship program, where you can get some help from one of our data scientists with making sure that your program is actually useful in real time and you get the best results you can. Thanks for helping me snazify my presentation, everyone. Loving the hearts and the arrows. Okay, so us at Peltarion, we're also here to help. So you can contact me directly at Anna.gross@peltarion.com to receive answers to questions or to find out more about any of the things I've said here today. Or just if you are working for a company and you think that you could benefit from doing a project with us, we also have a services offering that we'd be happy to talk about as well. So I hope to hear from you more in the inbox, and that this lecture has helped you get a better understanding of the opportunities that we have ahead of us with AI. And yeah, start making use of them yourselves. So I think we have about 5 minutes for questions. So if you want to post any questions in the left-hand corner, or even unmute your microphone and ask them, then please go ahead. Thank you, everyone. Thanks for participating. I will be happy to send the slides to Natalia, and she can send them on to all of you. Yes, there are some limitations. We don't have. There are a couple of models that we don't have on the platform. So if you wanted to do something very specific that we don't have at the moment, then you'd need to do that off the platform. But for a lot of very standard setups and a few more advanced ones, we that is all on the platform now. So it's a pretty quick way to get started if you want to build a proof of concept or see what you can do with it. There are other platforms as well. There are some that work more on the machine learning side. So you remember where I spoke about the differences between working with tabular data and sort of unstructured data. Unstructured data being images and text and all of that. So not just data that's poorly organized, but just all kinds of data that isn't tabular. But there are some platforms that are better for machine learning where you can go to explore that. Can we use BERT for detecting hate speech? I would say that that would probably be a really interesting model to try to build. So if there are patterns in hate speech that you think are reasonable to find, then we should definitely be able to use BERT for detecting it. I think the thing with data science projects is that very often it's hard to say what's doable until you've actually tried it, which is both what a lot of people find really frustrating with it, but also what's I mean, it's quite interesting because you can try so many things and actually get results that you didn't think were possible. So, you know, it's both an upside and a downside, but a lot of the time you do just have to go in and try it to see if it works. So if you have a hate speech data set, or if you want to try with one from Kaggle, I actually think there's one on there for bullying, which might be a slightly similar problem type. Then you can try to upload that data and see what kind of results you get and if they're good enough for the type of application that you have in mind. So that would be one way to go about it. Can we use AI in real time for websites? Absolutely, especially with such a snazzy deployment. So yeah, if you want more information, depending on the type of problem, you know, just send us a little bit more information. I'll be happy to get back to you on that. What are the most important concepts to learn for a newbie in AI? Okay, so this is a really good question to ask me because I have been a newbie in AI for so long. I would say that there is so much to learn, but also that the best way to learn it is to start doing. So once you've started building a model and you start exploring like, oh, what happens if I change the batch size, then that might be a really good time to read about batch size. Or if you have a new type of problem type and you say, for example, I want to generate new images, what type of model exists for that, then you can read some papers on that. So I would really, really advocate for an experimental approach when learning about AI. So learn by doing, inform your own sort of development with the types of things that you read. You might want to look at videos of what other people have done or read some papers. Yeah, our blog is also a good resource, but obviously I would say that. So there are many, many good resources out there. Language translation. So right now we don't have the functionality where you can generate new sentences in the platform. That's something that we can't do. So the Peltarion platform is not right for that at the moment, unfortunately. How to scale with the platform. On-prem deployment? No, we don't do on-prem deployment, unfortunately. We own everything we do is in the cloud. But we do have some really good policies for how to do that in a secure way. And if you want to talk to us about that, I'm happy to reply in more depth in an email with some input from our security experts as well. Can you link AI with other programming languages? Does that mean other programming languages than Python, or just other than the platform? Yeah, I'm not the best person to ask that question to, unfortunately, because I've mostly worked in Python, and I'm also still learning that. So that's a little bit above my level of expertise. But if you want, you can send that to me in an email, and I'll be able to find the right answer for you. No, no need to apologize. I'm very happy for all these questions. Okay, I'm really grateful that you all stayed with me for this super quick introduction to AI. I think we covered a lot of ground, so I'm really happy you stayed with me. And thank you also for your questions. So we will hopefully hear more from you via email if you have more questions. And if not, then thank you so much. And thank you, Natalia and Beetroot, for hosting us today. Okay, have a nice day, everyone. Thank you so much. Bye.